Hey, John, you're muted.
Okay, I am now unmuted. I'll spare you all my frantic preparations here. And now I guess we are indeed ready to go. Okay, well, welcome everybody. We're going to cover an awful lot today because yesterday we built a good foundation to really dive into machine learning. Yesterday was mostly about big data, but we'll find out that those techniques prepared us well to now really spend today getting more and more sophisticated in the techniques that we're going to employ in machine learning. We're going to start out with fast, actually, with a system, a recommender system that really does demonstrate some important, relevant, leading-edge classical machine learning techniques, and we'll find that that transitions very well into this afternoon's TensorFlow, which is going to be using absolute leading-edge deep learning techniques with neural nets, and they'll mesh together quite well. And we'll continue to build on the principles that we started with yesterday. So yesterday I left off with the notion that these things are kind of coming together as a theme because AI, and I won't reiterate the whole slide slowly because we went over it yesterday, AI as a field has developed from largely, and not long ago, being a well-balanced collection of classical machine learning techniques, mostly based upon very well understood and well analyzed and well behaved statistical and probability algorithms in some sense, and deep learning, which was just a little novel exotic technique, has really taken over an awful lot of the field because of big data. And that's something that I've just stated at the moment, but you'll appreciate it as we dive more into these techniques, how important big data is to make it possible to do these things. Big data combined with one other piece, which is GPUs, and that will also all make sense. So by the end of today, this picture and how it came about will all be clear to you instead of just something that you have to take my word on. Okay, but let's start out with our own application now, which will be a little bit less of a toy problem than the ones we did yesterday. Matter of fact, it won't really be a toy problem at all. It will be very much a real application. We're going to build a recommender system, which, as the name suggests, is an application that recommends things to you. The obvious applications, we're all familiar with these. I mean, they show up all the time every time you're on the internet, something somewhere, whether it's an ad in the background or whether it's your application actually being helpful on Amazon, recommending a product to you, or Netflix recommending a movie to you. These things are all based on the same principle, which is that we want to take the limited amount of information it knows about you as a customer and figure out as best it can the things that characterize you to target appropriate products at you. So in this case here, we're going to actually finish with this morning with the Netflix competition from about a little less than 10 years ago, where Netflix said $1 million to the person that can best help us improve our movie recommendation algorithm. And we're going to use the very same data sets that were used in that competition, and we're going to use the technique that was core of the winning entry, and still remains one of an ensemble of techniques that are very important today to Netflix to do this, as well as many other applications out there that are related. So I think the application speaks for itself. I won't belabor the point there, but the approach that we're going to use is going to be, I think, for many of you, surprising and interesting. And intuitive. That's the neat thing. It's one of the reasons I like this problem. By the way, for any of you that are following along on the slides, well, I expect all of you probably are following along on your own copy of the slides. Make sure you do have the updated slides from this workshop, because as we move through today, these materials in particular have really been updated a great deal from previous versions of this event. This one a little bit. As we get deeper into it, a little bit more. By the time we get deep learning this afternoon, some massive revisions. So, and it reflects the fact that the field keeps changing, and we try our best to keep up to date. So please make sure you have the current slides from this month's workshop, and not ones maybe you grabbed a week or two ago if you're really one of those early preparers. Okay, the Netflix competition files are very straightforward and simple. Another reason I like this, they're in a human readable text file sitting there in your exercises directory. No need to jump into there just yet. We'll have time to look into it later. So you probably want to follow along with me, more paying attention than trying to line by line copy what I do. Although for those of you that are really comfortable doing so, you're welcome to fire up an Interact shell and play along. But I would suggest you pay attention mostly at this point. The files that are sitting there in your exercise directory are nice human readable text files. And the most important one is the ratings data set. But there's another one sitting there which we won't really use until the very end, and we want to really make a nice output for our application and have it list the movie titles and everything appropriately. And that's the movie data set. And it basically gives for every movie number, a movie title, and some other information. As I said, we won't really use this until the end, because instead what we're going to do is we're going to treat the movies just by their numbers as a good label in our algorithm. We'll call Dangerous Minds will just be movie 31, and that'll be fine for all of our data shuffling and management. At the very end, when we want to show the user the actual recommended movies or their top 10 movies or whatever, that's when we'll attach the movie name to it. And so we won't care so much about this, but what we will care most about, what will record everything we're going to do, will be the ratings data set, which tells us how much a particular user liked a particular movie. So the ratings data set is a big file full of user numbers. So the first number is the user number. Every user's got a unique number. The second number is the movie number. So movie number 144, if we go up and look in this file, it might be Purple Rose of Cairo. Whatever it is, we can just treat them as movie numbers through most of our work here. The movie rating for that particular movie. And the last thing is a timestamp, which we're going to disregard because it turns out that's not that useful in deriving our recommendations. But the user, the movie that they reviewed, and the movie rating that they assigned to it from 1 to 5 stars will be key to everything that we're going to do. So that file is one that we're going to read in early on and work from there. Now, if we look at that file and we plot it out, it looks like, in a sense, a spreadsheet, a big, sparse, very sparse spreadsheet. It's very sparse because this spreadsheet has the users and all the movies, and any given user has only seen a tiny fraction of the available movies. Netflix might have hundreds of thousands of movies in this database, and they do it in the large version of the database. It's got lots and lots of movies, and a given user's only seen a tiny fraction, so there's going to be very sparse entries, even sparser than this particular graphic suggests. And that makes perfect sense, I hope, to all of you. Our objective is going to be to generate a very dense matrix to fill in all the missing entries, in essence, so that if a user said, hey, for all of the many movies I haven't seen, what do you think I would think of this one? We could tell them what their projected star rating is. And we'll also use this data to say, give them their top 10 movies. We can go through this for any given user and pick the top 10 star ratings that they would have for the movies. And so we're going to fill in this sparse matrix. We're going to try to infer the missing data from what they've given us. And this makes perfect sense in an intuitive sense. If you think about it, for example, what I cite up here is that if a user likes Annie Hall and Purple Rose of Cairo, which are both Woody Allen movies, then even though we don't know that they're Woody Allen movies, so the database doesn't have that information, right? It just has users and ratings. But if lots of other users that like those same two movies also like Zelig, then we could recommend that. We could notice that pattern. And I haven't said how we'll notice that pattern yet, but I'm just telling you that if you went through this as a human being even, and you notice that pattern, that everybody that likes these two movies seems to like this one, then you can recommend that movie. Now, what you've done is actually prize some hidden information out that's not really in the database. You've figured out that all three of these movies are Woody Allen movies. This user seems to like Woody Allen movies or might like Woody Allen movies. That information isn't in our database. It's a latent effect. And we'll come back to this principle as we go along here, how we're teasing out information. But first, we'll look at our technique for doing this, and then we'll see how it manages to tease out that information. Our technique for doing this is, first of all, it's going to start out with what seems to be something motivated by just making our incredibly large matrix manageable. We've got to come up with some scheme to deal with a matrix that could be, remember, the size of the matrix, or our matrix here, is the number of users times the number of movies. And so the users for Netflix could easily be tens of millions, and the movies would be easily hundreds of thousands, if not more. And so this matrix is enormous. It's not something that you could juggle around in memory very easily, and so, or if at all. So what we want to do is we want to come up with some approximate way to keep this in memory, some compressed scheme for our matrix. And we're going to be able to do that by approximating this matrix with a U and a P, which we'll find will come to stand for a user and a product matrix. we're going to somehow come up with a scheme that gives us these two smaller matrices that will give us any element of this big matrix. Now, once again, linear algebra is the standard language of machine learning. And so if you really want to get, comfortable and good and proficient in machine learning, you should get comfortable with basic linear algebra. If you want to be an expert in machine learning, you should get comfortable with more advanced linear algebra. But at any rate, for today's purposes, even if you're very, very rusty on linear algebra, the only concept that we need to dredge up is matrix multiply. So I hope that all of you can remember or just recall right now at the moment the principle of matrix multiply, which is to get any given element in a matrix. When you do a matrix multiply in the resulting matrix, you take this. So if we have an element here that's in this row, this column in this row here, what we do is we find the appropriate row here and the appropriate column here, and we the appropriate column here, the appropriate row here, the appropriate column here, and we multiply those two together, and that will give us the new element here. And that means the width of this matrix has to match the height of this one, because we're doing a dot product. We're multiplying this row by this column. And so they have to be the same length, of course, in order to do that appropriate multiply add operation. But that allows us to generate any given element that we want in this matrix here. Now, it should be, hopefully obvious to you that these two smaller matrices here, because we haven't said yet how skinny this one is and how shallow this one is, but they could be very skinny and very shallow, so they can't possibly have all the information to reproduce every element accurately in the original matrix. This original matrix has a lot more data points to it, potentially, if you want to think of it that way. That's the whole idea here. We're trying to come up with a compressed way to have two smaller matrices. And that right away gives you an indication that this is an approximation. This is a lossy compression. So what we're coming up with is a lossy compression scheme that will allow us to have two smaller matrices that we can actually use to generate data points for an enormous matrix that can never actually exist because it's too big to fit into memory. And so that's our scheme here, our lossy compression scheme. Now, what we're going to find out is in the process of being lossy, it's going to smooth out the data points in this original matrix. So in the process of not being quite faithful, it's going to smooth things out. Shouldn't surprise you if we took a JPEG image, right? JPEG's a lossy image compression scheme of, say, very, very sharp points in the night sky. If we took the Hubble telescope, which can give these amazingly precise points, looking at stars in the sky, and we take a JPEG, you would expect that the JPEG is going to smear things out a little bit. If we zoom in on a JPEG, things that were is our smaller U and P matrices are 10.
Hey, John.
Yes.
You froze there for about 15 seconds.
Well, that's not good because several reasons, one of which is this is some key information here. Thank you, Tom. Please continue to let me know if there are issues like that. So what I was saying, and it's a key point, and it's a key point not just for this application, but for machine learning in general, was that the process of doing lossy compression on this matrix is going to smear things out a little bit. The example I just used was that if we take a JPEG of a photograph that's very sharp, if we take a Hubble telescope image that might be 10 million pixels by 10 million pixels, and we take and look at that in as a raw image, we'll see that sharp stars are very sharp points. If we take instead and take a JPEG of that image so that we can post it on the web, it needs to be a lot smaller. That JPEG, when we zoom in on it, the stars are going to be smeared out. That smearing out is going to be in general, it does seem like it's a bonus for us, right, to have something that's a little bit less focused. In this case here, we're going to find out that smearing out that these two approximation matrices gives us smears out our sparse matrix and gives us good projections for all those missing data points. Now that seems kind of miraculous that this seemingly unattractive feature and undesirable feature that we're smearing out our data points with our lossy compression scheme is giving us actually a bonus of projecting valid missing movie information. But as we'll see, not only does it work and does it work well, but it also represents a general theme that I began to touch upon yesterday, and will come back to us again and again today, that learning can be very much thought of as compressing data. What you learn about the world is very much you learning to think of a reduced representation. If I say, what does a cat look like? And you picture a cat, or if I were to show you a picture and say, is that a cat? it's not because you've seen a picture of every cat in the world. It's because you've thought of a way of condensing what a cat actually is down to a set of features. So if I show you a picture of a purple cat, if we were to take a cat and paint it purple, you've never seen a purple cat before, but you could easily identify it as a cat because you've compressed the knowledge of what a cat down into a bunch of features, not because you've seen a lot of purple cats. This idea that knowledge learning is compressing down your model of the world is key to not only this, but all of machine learning. And it will come back to us today, but it's one of the reasons why at first, even though it seems somewhat miraculous, that this compression scheme for our movie database gives us our projections. It seems miraculous at first, but then as a machine learning person, it should start to kind of seem not that miraculous. That kind of makes sense. So we'll see this happen as we go through this model, but that's our idea. So that's the foundation of what we're going to do. Now, when we do matrix factorization, in other words, breaking a matrix up into submatrices, in linear algebra, we'll find that there are many options to do this. And by the way, once again, our dimensionality reduction badge has popped up here. As I said yesterday when I introduced this topic, dimensionality reduction is an important component of machine learning. It's keep coming back to us as well, very much related to this idea of compressing our knowledge down. So here we're seeing another version of dimensionality reduction. You can very well imagine, well, I'll explain it explicitly here, that somehow we're doing a dimensionality reduction if we're taking this very large R matrix and we're compressing it to these two smaller skinny matrices here. And that is the case. We're going to take what for a given user would be a very long vector. It might be a vector that could be 200,000 long because that vector is going to record their star ratings for every movie that they've seen or movies that they haven't seen. So that would be several thousand long, or excuse me, several 100,000 long in the case of Netflix. When we're done for the user, we're going to have a vector that represents them. It's going to be very much shorter, maybe very much shorter. We're going to find out that this value might be on the order of, say, 12. So that is, in some sense, a pretty explicit dimensionality reduction of information about that user. So we're doing this, again, as dimensionality reduction in a way with a technique that we're going to use. Called alternating least squares, but I'm getting ahead of myself. The important thing to understand right now is that we're going to end up with these two smaller matrices that will give us, for any given element in our original matrix, will give us a value of it. It'll be an approximation of that value. It can't be exact because we got a lot fewer elements over here, but it will give us, hopefully, a close element. So if we go into our original sparse movie database here and we look at one of these points here, we can reconstruct that by going back to the appropriate row and column here and doing a little multiply of each row and column. And so again, that's pretty much the only linear algebra you have to recall for this particular application, is how matrix multiplies basically work. Now, we get to choose how skinny or how tall these two matrices are. It has to be the same number for both to make the matrix multiply work out. We're going to call that number K at the moment here, or the rank of the matrix. We get to pick that. That's a user parameter that we get to choose based on, well, we'll see. We're going to have to choose it empirically based on performance. The bigger it is, you might think the better the approximation would be. That would be a largely valid assumption, but it's going to take more memory up. The smaller we make K, the skinnier we make these matrices. They'll be much easier to fit into memory, but you might think your approximation is going to be worse. So this K value here is up to us to choose. It's going to end up representing the number of latent effects that we can capture. We'll come back to that term. I've already mentioned it a few times in passing. This application will really expose exactly what a latent effect is. This will be the number of latent effects that we can capture. So this is our scheme here. And once again, from linear algebra land, we are given a number of different ways we can decompose a matrix. However, with matrices this large, we're going to find out that there aren't a whole lot that are going to be viable. For example, if you go back to, if you're comfortable with linear algebra right away, something like SVD or singular value decomposition comes to mind. And if you're not comfortable with it, you go and look up some recipes for decomposing matrices. You'll see a lot of options, but you won't find many of them that are meant to work with matrices that are millions by hundreds of thousands. The technique we're going to use is called alternating least squares, and it does indeed turn out to be practical with these enormous matrices here. But this is the idea of what we're going to do. Again, you can think of it as we're starting out, we have to find a way to juggle this enormous matrix in memory, so we have to come up with these reduced representation, and then magically out of it will appear our representation scheme. So,
Couple questions.
couple questions. Okay.
Any reference or link to public description of this data set would be helpful.
Okay, that's not a reasonable question. Besides the fact that you actually already have it sitting in your directory, so you do have access to it. I didn't embed a link here because it's sitting there already, but that's reasonable. If you look up the Netflix, by the end of today, I will come back to kaggle.com, which is a site that has all kinds of competitions that has the data set there. So for those of you that don't want to scribble a note right now, we'll come back to it at the end of the day, a site that has all kinds of sets, including this one. This is a fairly well-known set because it was $1 million competition. Otherwise, if you Google Netflix prize data set, I'm sure many alternative sites will come up that will give it to you. So the data set's pretty popular. So off the top of my head, I don't remember a URL, but you'll have no problem finding it. And at the end of today, when we come to kaggle.com, that site in particular, if you enter it into their search engine, you'll find not only the data set, but several ongoing competitions to do what we're doing here today. Again, no URL off the top of my head, but if you have any difficulty finding it beyond that, let me know. Let me see if your other question, Steve, here is, do two smaller matrices have complete data points? The two smaller matrices, we hope, if by complete data points you mean, are they dense? The two smaller matrices are going to end up being dense. They're not going to be sparse like the original matrix. They're going to be dense. If that's what you meant by it. If by complete data points you mean, do they have enough data points to reproduce every data point here? No, they don't, because it's a lossy compression scheme. So they will have, together, the two of these will be much smaller than all the data points that could potentially be in R. So that's answers two questions there. I hope one of them was yours exactly. Another question was, what method did you say we will use for matrix factorization? We're going to use alternating least squares. We're going to look at that slide in a few here, and so we'll jump into it explicitly. So I will say no more about that right now, because we're going to say a lot more about that very shortly. Okay, once again, to come back to what we're doing here is, this is, I hope, in an intuitive sense, existed, and you had never heard.
John, you froze again there for 5-10 seconds.
Okay, I'm sorry that this is going on there. Matter of fact, Steve, can you confirm that that's happening universally? I'd like to believe it's just happening to Tom. And not
No, it was about 5 seconds that time.
Oh, well, that's a shame. Okay, well, as I was saying here, I don't think I've said anything critical in those 5 seconds, but as I was saying here, if you want to look at this again from the intuitive sense, this shouldn't be that amazing what we're trying to accomplish, which is to guess suggestions for users based upon what we do know about them. If you were a clerk in a video store, a Blockbuster back when they were around, and you paid attention to what your customer's doing, you would have noticed patterns like people that rented E.T. and Raiders of the Lost Ark and Jaws and Close Encounters, might also end up being the same people that rent Jurassic Park. Now, you don't know that these have a common director. Maybe you don't know. I mean, let's assume that you don't know that these movies all have a common director. But you start to notice this pattern. That means that you're finding from what's going on out there, you're inferring some latent hidden data, some pattern amongst things. Again, as a human being, that shouldn't surprise you, right? You begin to see these commonalities between people that are renting things. And so this latent hidden information, this latent effect, is the kind of information we're going to tease out with our alternating least squares. Now, it wouldn't only be director. You could also notice the same things by seeing people that like common actors or common genres. You could say, oh, this person rents all sci-fi movies. Even though you don't know that, you just notice that the movies that they rent are all share in common the same pattern as somebody else that rents some subset of those movies. You're beginning to learn that those two people are sci-fi fans. And you can recommend things based on one user or the other users that are sci-fi fans. So you're finding these hidden things, and you're using them as ways to represent people in a compressed version. Instead of saying, hey, Mary likes these dozen movies, you can instead say, Mary likes documentaries. That's a way you think of somebody. This person likes documentaries. This person likes science fiction. This person likes old black and white movies. So you can begin to think of people, and we all do this naturally, you think of people in these reduced ways instead of thinking of them as long lists of details. So again, the notion that machine learning is compressed ways of thinking about data should start to appear normal to you. It's the way we do learn things about the world and about each other. And that's what we're going to tease out of our data here. So our matrix factorization scheme here is going to allow us to pick how many, or going to require us to pick the width of the matrix, which is also going to be how many of these latent effects we can accommodate. So for a user, that's going to say how many things can we know about a user, their genres and director preferences and actor preferences. Now, none of these columns here of our latent effects are actually ever going to be something we can say, oh, this is genre and this is actors or directors. This is another thing about machine learning that you should get comfortable with, which is that these latent effects, these hidden things, are very rarely as explicit as we would like them to be. This is true of what we're going to do with deep learning even more so. As a matter of fact, it's one of the central research problems in deep learning is trying to determine what these latent effects actually represent in an intuitive sense. The machine makes sense of them, whereas we as human beings would like to translate them into human terms. So in our case here, these latent effects are going to end up representing things about the user, but I can never come in here and say, yes, this column represents genres for the user. So that's, again, a lesson that's universal to machine learning, very hot research area to try to make as much sense as you can out of it. But in our case, we will at least get to choose how many latent effects there are embedded in the model by us picking a value for K. Okay. Now, before we jump into this alternating least squares thing that I've said is going to give us a representation, one of the things we need to do is to define an error because we're going to come up with an approximation. How good is an approximation? So defining an error, as I said yesterday in machine learning, is a core part of defining your problem. And we're going to find this applies to every type of problem in machine learning. Yesterday, it applied to clustering. Clustering, we kind of had an obvious suggestion for what the error could be. We said that for k-means, we're trying to find clusters. So geometrical distance is probably a good way to figure out the error. How far are points from our found clusters? Makes sense. However, it's not always so obvious. For image recognition, for example, which we're going to get deeply into this afternoon, if we have an algorithm that's trying to recognize cats and dogs and horses, which, by the way, is very much an algorithm that we'll have as an exercise, suggested exercise problem for you. What if we have a picture of a cat and we tag it as a horse or a car? Is horse works? Seems to me like tagging a cat as a horse isn't as bad as tagging it as a car, but how do I quantify those kind of errors? And so it's not always obvious how you put a number on an error. With our recommender, what we're going to do, since we're working with matrices, is we're going to say that a good error term might be to take our original R matrix and take our approximation matrices, and for any given element, we're going to take the mean square error between those two. We'll add up all the elements together. So we'll take any given element. If our original R matrix said something is 1, and our approximation matrices that we end up, when we go back and look at them, say that something is 3, then we've got a difference of 2 there. And we'll square that to get 4 so that we don't have any negative numbers. And then we'll add up all of those errors across all the elements in the matrices so we cover all the elements. That total error, that total difference there, the mean squared errors, will be what we call our total error. So a mean square error, by the way, is a very common, simple, straightforward way to come up with errors whenever you've got a bunch of numbers to compare. That shouldn't be a surprise to any of you. We're just going to apply it to all the elements simultaneously of our matrix. So that's our error. That's good to have that first, because now when I start talking about what our approximation scheme is, I can sensibly talk about how good or bad it is. Otherwise, if I don't have an error, I can't talk about how well I'm doing on any of these problems. So machine learning, having a good error is key. Okay, well, that means this is the actual definition of our error, as I just stated right here. I said our error is taking our matrix, and then we're going to take the difference element by element, which is what this kind of notation right here means typically, but it just means element by element. We're going to take the difference between the R matrix and the elements generated by the U and P matrix. So this is to any given element. The R matrix, we're handed the element because that's our given data set. The U and the P matrices, we have to multiply together to get that element. And then we're going to take element by element, take the difference squared. We're going to add those all up. Now, we're going to introduce here a concept that we started to touch upon yesterday, which is a regularization term. And this is a standard term that you want to get comfortable with in machine learning, which helps us to discourage overfitting, which is a term I'm about to define very explicitly for you, so that we don't drive our error too low at the expense of getting an odd fit on our data. So I've just said a lot of loaded things in that sentence there, and it's important that we pull that apart because this is a key concept again in machine learning here. How can we have too little error, which is what leads to overfitting? Well, we've already talked about this. We've introduced this yesterday with our clustering problem. We said with our clustering problem where we had 5,000 points, that if we told the clustering algorithm, find me 5,000 clusters with 5,000 points, we could always have an error of 0. Now, we haven't really learned anything. We haven't found any real clusters of our data, but we have a very low error, right? So we can easily delude ourselves into thinking that we're being successful when all we're really doing is driving an error inappropriately to 0. So that from the clustering problem, I hope that already seems like, okay, it's not an outrageous idea. But here is maybe a better notion in general to see how this works, which is that if we're back in high school and we're doing a science experiment to figure out how springs work or how things fall or whatever, and we start graphing data and we get some data points that look like this, then you might, based on those data points, project that you've got a curve, maybe a quadratic curve that fits your data that looks like this. And that might be a reasonably good idea, knowing that, you know, lots of things in nature have this quadratic kind of fit to them, and it fits the data points pretty well. But you might be extra clever because you took an algebra class that day where you learned that if you've got 5 points, you can always fit them perfectly with a 5th order polynomial. So you might say, I can do a better job of fitting this data by using a 5th order polynomial. And that's true. With a 5th order polynomial, you can always hit 5 points perfectly every time. You can drive your error to 0. So aren't you clever? But what you've done now is you've got a curve that's a lot more complicated looking than the quadratic fit, which didn't fit perfectly, but kind of was simpler. So now we've got this curve right here. And right away, you might be able to roll it out right away by saying, hey, we got some points here that can't be true. We know that things aren't this unstable. We know there are never any negative values. So you might be able to guess that that's not right. Or you might fool yourself into thinking, hey, look, I've got the smallest error of anybody in the class in my fit to the data. So this idea that we can often just by picking a more complex model, drive our error to 0 at the expense of fooling ourselves is, again, very common. And we come back to this idea that we would like to somehow prevent this overfitting by some regularization scheme. And therefore, our data, our model that we come up with will generalize, will actually work better in the real world with data that we don't have in hand. The future points that we haven't captured will fit better if we do this well. So you can think of this as the Occam's razor. Occam's razor says the simplest hypothesis is probably preferable, the simplest solution, and that's equally true here. You can think of this idea of let's not come up with an unduly complex model just to fit the data perfectly. That's Occam's razor of machine learning, and that's what we want to do. So we need some method here in almost every machine learning problem to prevent this. And again, these are the terms that you will see. You will see that you want to avoid overfitting your data. And anytime you're overfitting, if you're confused by what that means, if you think back to this example, I think this one will always steer you right, which again is that you can easily, with a bunch of data points, drive the error to 0, and it's not valid. So you want to avoid overfitting by some kind of scheme that usually is called a regularization scheme. There would usually be a parameter that you can adjust to determine how harsh you will do that. In our case,
Hey, John. Hey, John. Sounds like you're talking in a submarine for the last 20 or 30 seconds.
Wow, this is bad. I'm sorry to hear that. Okay, let me recap this quickly then.
And we have a question.
Yes.
Wouldn't this be accounted for by making sure we take a small enough K, make our matrices skinny enough?
That's an excellent question. So when you start thinking about avoiding overfitting, you can say, okay, well, if we pick small k, we're going to have a way right there of preventing us from fitting our data perfectly. But that may also cost you in that case directly in terms of the accuracy that you need to get meaningful fit at all. So saying that we're going to intentionally make things, so that's excellent thinking, by the way, that's excellent thinking. But in this particular case, saying that we're going to limit our k as the way of doing that might also prevent us from coming up with a reasonable approximation. So we might not be able to even come up with a working approximation by using K as our parameter to do that. But that's good thinking, and it could be an answer. Turns out, like I said, in our case, it won't be a good answer because it will prevent us from being able to pick the right K to capture enough latent effects. So instead, what we'll do is we'll introduce a separate parameter here that's going to more directly allow us to avoid overfitting. But that's great thinking there. So instead, what we're going to do, instead of using K as our parameter, making it do double duty as our approximation parameter and our regularization parameter, we're going to come up with a separate scheme here for regularization. It's a little bit more explicit. Instead, what we're going to do is we're going to penalize any very large U or P values. With our previous polynomial fit, what you might do is you might say, we're going to penalize higher order terms. So, and that's exactly what's done very often in schemes that use polynomials to fit, is you have a term that says a squared term's okay, but a cube term is a little bit worse, and a quadratic term is even worse, and a fifth order term is really bad. So you try to penalize using higher order polynomials. In our case, we're going to penalize using very large particular elements in our array. So if any given element in U or P is very large, we're going to say that's not what we want. We don't want to have really spiky elements. By avoiding really spiky, huge single elements in U or P, we're going to smooth things out a little bit in a way that turns out to work pretty well for this problem. And again, a lot of these regularization schemes are found empirically. People come up with an idea and try them and see how they work. And in this case, this is one that's successful. But it's not the only one you could think of, but it's one that works pretty well for these kind of problems, to say, let's not have really spiky values for U and P. And again, you can think of this as our R matrix values are star ratings. So they're all between 0 and 5, or 1 and 5, I guess. They're 1 to 5 stars. And so we don't want U or P maybe having values of negative 12 million and 100,000. But that might happen as we're trying to approximate this R matrix. You might find very spiky values, but that would tend to then overfit the data. So this scheme right here is the one we're going to use. It works pretty well, but if you want to justify it exactly analytically, good luck. You're not going to be able to do that. You're just going to be able to say, these are some intuitive reasons we think it works, and it ends up working pretty well. So this parameter, though, lambda, is going to allow us to tune how much we want to penalize. If we set lambda equal to 0, well, we're back to just our original fit this as best you can scheme. If we make lambda very large, it's going to have a huge penalty and tend to make all the values very small and smooth. And that might work well to prevent overfitting, but it might make it hard to fit the data well at all. So that's lambda gives us the ability to play with this idea, with this scheme, to turn the power of it up and down. So then at the end of the day, then this is what our new error is going to actually look like. It's going to look like for any element. So here I've drawn it out element by element. If you want to step through this, we're going to take our original R values that were given in our data set. We're going to take, and with our U and P arrays that we're approximating this with, we still don't know how we're going to find them yet, but assuming somebody hands us one and says, I think this is a good approximation, we're going to take the difference element by element, and we'll add all of those up, the squares of those, all of those up, and that would be our first guess at how to do the error. But now we're going to introduce this additional term that says, then also take for all of these and take the absolute value of each of these elements here squared and add that into the error. And that's going to make these values tend to want to stay small if we want to reduce the error. And by the way, if any movie is unknown, if a movie hasn't been rated, we'll just set it equal to 0. So this now defines our error term right here. But it also, if we start keeping track of things we're juggling here, we now have a couple of parameters that we have to pick ourselves intelligently. K, the width of our matrices, and lambda, our regularization parameter. So these parameters that we have to choose to make our schemes work well are hyperparameters. We have to choose them maybe based upon some decent initial guess, but mostly based upon some empirical feedback as we experiment around. Almost never based upon some calculation that you can do explicitly. So the search for good hyperparameters is a big part of machine learning, and in some sense where almost all of the effort, the sweat really goes. The repeated trial runs to try to home in and get a scheme that works. So the search for hyperparameters is a huge part of machine learning. And again, yes, Steve?
A couple things. Is Wij normally 1 if the cell is not blank?
No, it will be 0. So if this, oh, if it's not blank, no, Wij, if it's not blank, this is going to be, yes, it's going to be 1. Exactly right. Yes, this is just 1 or 0. So it's just 0. It exists only to zero out the cells that are blank. Yes, good question.
And you might want to look at the last comment. Is
Let's
lambda a parameter or a function? Why does the error not just end in? See that?
Oh, lambda is a coefficient here. It's just a scalar variable. So lambda is not a function. So yeah, the notation here is a little bit ambiguous. Lambda is not a function. Sorry. So lambda is just a scalar number, a variable coefficient that we're going to pick. It's usually going to be something less than 1. But it's a variable which is a scalar. This is absolutely not a function here. One could think of a regularization function and get more complicated, but that would quickly lead us into very complex, probably force we'd never emerge from. So lambda is, fortunately for us, just a number. Good question, though, because again, a notation for these, a notation is rarely sufficient to be completely unambiguous in machine learning. So there's a context a lot of times when you look at something. Once you read enough papers, you look at something and realize you're seeing a lot of context because you understand the problem. But if I just take an equation out of context, sometimes it's extremely ambiguous as to what's going on. Okay, now we finally come to how we're actually going to find these U and P matrices.
Another quick question. Is it usually a small fraction so penalty does not overpower the other term?
That is exactly the case. It usually is a fairly small term. We're going to find out what our good starting point is. But if you said to me, how can I justify that out of the gate? The answer would be, it would be very difficult to do. So instead, what you do is you really do have to explore a range of scales, maybe even orders of magnitude. If you're the first person to try the scheme, you might be all over the map trying to figure out what the value is. And then once you get something working and you publish a paper and people like your ideas, then you have a jumping off point for other people to begin to explore how they might use that scheme. Again, that's a very, very important part of hyperparameters. It's maybe the last slide I have all of today. It loops us back because we'll find so many interesting hyperparameters as we go along. And then we'll come back to, the search for hyperparameters is a big part of modern machine learning. And so what the initial value should be, people often say, well, how do I know where to start? And the answer is you hope that somebody else has at least given you a reasonable guess as to where to start, because otherwise you do have your work cut out for you. You might be investigating a wide range of values. So your question is a very good one. It's going to come back with almost every hyperparameter that we dip into today is what's the starting point for that? And the answer is almost always going to be, well, I found something that somebody else used in a related problem as my jumping off point. And that indeed is the standard way of approaching these problems. You hope somebody did something kind of related to give you a jumping off point. Okay, the scheme that we're going to use, again, we've defined everything we want to do here, except how do I actually find these U and P arrays? So let's say that you do say I want K to be equal to 10. Now find me a U and P array based on R. Well, how do I do that? And if you start to sit down and write out a bunch of equations on, you're going to find very quickly that you have, because of the enormous size of these arrays, you've got millions of equations that are nonlinear, and it's a very, very difficult and tractable, actually, problem to do exactly. So we need some kind of scheme that will iteratively home us in on it, and we're going to find out that alternating least squares is the answer for us. You might think if we had a small problem, there are other schemes that we could use to get there, like stochastic gradient descent, which we'll use for other problems later. But in our case here, we've got billions of parameters here. We need some scheme that is capable of dealing with these enormous and sparse arrays. And alternating least squares is good not only because it works well with enormous sparse arrays, it's also good in parallelizes well. And that's critical. In the modern world, if your scheme if whatever you're doing doesn't parallelize, you're not really in the game, because everything we're doing today better end up working in a data center or it's not going to be competitive. Everything needs to be parallel anymore, or it's really not interesting. It's good on your laptop, but unless that's what your ultimate application is intended to run on, good luck. So ALS parallelizes very well. So it's good for a variety of reasons. Let's see how it works. And whoops, let me see here. I guess I did add, like I said, a massively new revamp of this material. So I'll explain it here how it works. I had a little slide before, but I didn't think it was that illustrative. The idea with alternating least squares, and by the way, because this is handed to us by Spark as an algorithm, it's a common algorithm. So it's handed to us by any good numerical library like this. So I didn't want to dive. I wanted to avoid diving into the details greatly. You can treat it as a black box if you'd like, and that's not unreasonable, but I'll briefly describe how it works here. The idea is that if we cheat by, if we look at us trying to solve that R is equal to U times P as an exact problem, and we write down the equations, like I say, it's enormous and it's unsolvable for practical purposes. However, if we really had a problem where R was given to us and one of the other matrices was given to us, like P, and we only had to find U, if we were given that problem, that turns into a nice, simple, solvable linear algebra problem. As a matter of fact, it turns into a regression problem. We could just use least squares to fit it. And that's a problem that comes right out of a freshman level statistics course. So if we were really given the problem of R and P were handed to us and we need to find U and fit it, we could do that. That's not a tricky problem. So let's pretend that that's what we have. Let's set U equal to, or P equal to some values. We'll start out with some random values, set it equal to some random values, and let's solve for P to fit it to this randomly initialized U. Okay, well now we have R and an approximation for P, but U is actually a bunch of values we dreamed up. Okay, well now let's reverse that process, and now let's find U based upon P being the correct values. And now we can home in on U by doing this least squares fit. And if we go back and forth during that process, we'll find that U and P slowly converge and iterate on being the correct matrices. And so at least for our approximation to whatever degree of error we define. So this alternating least squares, that's where the name comes from. We're going to alternate and do just a least squares fit, pretending that the U and P arrays are actually, one of them at least, is actually correct already. That will get us there. So that's the scheme, and it does work, and it works at large scale, and it will converge on a reasonable approximation, at least within whatever error level we fit. And we'll have to go back and forth and iterate it to get there, but it will work. So here's our plan. Here's our overall scheme. Is we're going to start out with this sparse matrix that's the movie database that we're handed. So it's what's sitting in your directory right now, a bunch of user ratings for movies, where again, it's mostly empty. Most users haven't seen most movies, of course. We want to end up with this dense matrix here. And so what we're going to do is we're going to come up with approximation matrices using alternating least squares. And again, you can treat this as a black box if you'd like. If my previous explanation didn't make any sense to you, well, that's okay for now. You can go look it up later. Hopefully, if it did make sense to you, it's because it's not that complicated of a scheme. If you want to dive into and understand it, it's not difficult. So that alternating least squares is going to give us these two approximation matrices here. And with that, we're going to end up with them making this approximate matrix that's going to smear out and become dense. And so in a sense then, in a very real sense, a very direct sense, it's going to fill in all of the missing user ratings in our database. And now we can tell for any given user what they would probably, hopefully think about any given movie they haven't seen yet. So this is our scheme. So I hope this makes sense to everybody. And if it doesn't, this is a good time to maybe ask a few questions. I'll take notice when questions pop up now, because this is where we're going to move forward from here. Okay. How do we initialize U and P's? I mentioned it quickly there, maybe too quickly, that we're going to use some random values to initialize them. Once again, random values are coming into our scheme. I'll come back to this when we actually start writing the code out in a few slides. So once again, in machine learning, where you think everything's very deterministic, we're going to find ourselves needing some randomness, and we want to make sure that it's not critical. You might say, what should my random values be, or is our solution going to be sensitive to that? And those are very good and important questions. We might have to investigate that a little bit, but we're going to start out with some random values to be defined. And again, we'll come back to that in more detail. Let's see, could we do backprop instead of no, backprop? No, backprop would not probably be, no, backprop with these large sparse arrays like this would not be efficient. Good question. It sounds like it might be, but it wouldn't be. This is dependent on how R is arranged. Well, in a sense, no, in that we could certainly mix our users up or we could have them in alphabetical order, or we could have them in random order, and we hope that we still get valid predictions. So it shouldn't depend upon the row ordering in that sense. Could we also use SVD? I mentioned earlier, SVD does not work with huge arrays. It's not tractable, and it's not good with sparse arrays. So SVD would not be very good here in this particular application. If this were smaller, if our arrays were smaller and denser, SVD would be probably our go-to. Okay. Training, validation, and test data. This
Does the
is
value,
really,
does the value of K affect the regularization and how?
oh, that's a good question too. And the answer is yes, it does, but how would be very, very difficult. Actually, it's impossible to tease out exactly. So this is where, if you start trying to dig into it analytically, the relationship between the two would just be very difficult to figure out. You could intuitively figure out that the larger K is, the better it's going to fit the matrix without spiky elements. As a matter of fact, if K is large enough, it can fit the matrix exactly. So K could be smaller. Excuse me, lambda could be smaller. If K is very small, lambda is good. There's going to be a tendency to have very spiky elements in a desperate attempt with too few elements in the U and P array to fit things. Things are going to get very spiky. So lambda is probably going to have to be more effective and get larger. But again, it's going to be fighting the fact that you're trying to still have a reasonable approximation. So there is this kind of inverse relationship between the two, but teasing out exactly would be impractical. And so we'll find it, but we're going to have to empirically play around with lambda and K to come up with good values. But to start to do our empirical testing here, or any testing, or come up with our final values, we're going to need to pay attention to another extremely important and universal concept of machine learning, which is having testing data set off to the side that's not used to actually create our solution. This notion of having training data and testing data applies everywhere in machine learning. This is your introduction to it here, and it's going to be very important. We're also going to find the notion of having some validation data. It's kind of in between testing and training data that's going to help us fit our hyperparameters, but not actually be used in our final test is going to be important. So these terms are important enough, universal enough, and screwed up enough by people in the real world that it bears a little bit of dwelling on this slide here. So the idea is that as we develop our solution, we're going to have this fear in the back of our heads that we're overfitting our data. We've got our lambda here. We don't know a good value for it. We don't even know if the scheme will work. And we've got our Ks that we're playing around with. So how do we know that we're not overfitting? How can we assure ourselves? Well, one thing we could do is, before we start fitting our data, we could take some of those points off to the side and keep them hidden, that we don't look at them at all. So they're in a box off to the side. We don't use them to do any of our fitting, to either find lambda or K, or even to do our training with alternating these squares. That test data is off to the side. In this case here, it's some user ratings that we know are real. There's some users have rated some movies for real. They've given them to us, and we're not going to use them when we come up with our projected values. We're going to keep those off to the side. We're going to do everything, and when we're done and we really think we know exactly what we're doing, so I think I've really fit the existing data well, and we got a great value of lambda and K, and everything's working great, our reality check is going to be, we can go take that test data that we've sequestered away, and we can now use that and say, I'm projecting with my existing scheme, I project that this user likes Star Wars with a rating of 4. Well, you know what? I have this data hidden away over here in the box, Star Wars. Let's pull it out. Oops, this user likes Star Wars with a rating of 1. This user hates Star Wars. So now I go, oh, I fooled myself. I think I've driven my error very low and I fit the data, but I'm fooling myself because it's not fitting the hidden data points that we saved off to the side. Or hopefully I look at the test data and go, wow, this is working great. We have a good scheme. So this notion that you have some data that you never look at until you're finally done is very important. It's called your test data. I don't even want to hear about your paper or hear about your results until you tell me how it works on test data. Because otherwise you could easily be fooling yourself and overfitting things with your clever schemes and your hyperparameters that really look good but inappropriate. When you tell me what your test data is about, now I believe things, because the test data I knew is objective. So that's why the test data is so important. Now, along the way, we're trying to find lambda and K, and we're playing around with those. It might be nice to have some data that can be used you can think of it as kind of your temporary, almost test data that we use as we adjust lambda and K. And that's some data that we set aside when we're finding U and P. So we're using the training data to find U and P. And when we're done and we think we got a good U and P, we can, and we're playing around with lambda, we can use that validation data to check. So it's kind of like some interim test data. Now, the reason you don't want to use your real test data is because if you used your real test data and mixed it in here to find lambda and K, then you could really be finding lambda and K that help you overfit the data. So lambda and k are also really part of your training process or any other hyperparameters you have. So your test data should never, ever be used till the very end. People get this mixed up a lot. They mix in the testing data. And by the reason, the reason for this is not that people are dumb. The reason is that data sometimes is very, very valuable. Data can be expensive, especially hand-labeled data. Netflix data is probably pretty cheap. You know, I got bajillions of users all the time rating stuff. But in a lot of cases, your data is very expensive. You've got hand-labeled images of tumors or something. You really don't want to, not use your data to train your model better and fit your data. And so this temptation to not set aside enough testing data or any testing data can be strong, but it's always a mistake. So you really always want to set this aside. So people make this mistake repeatedly, though. They just don't set aside enough testing data. So what proportion should you set aside? And again, this is the kind of thing that might seem like there's some obvious analytical answer, and there's not. And you'll find that this varies. So there's some rules of thumb that you can get from people maybe working on similar applications to you. Generally this might range from maybe 20% to 30% of the data, something in that range. But there's really no analytical way to say exactly what you should set aside. So instead, you kind of, again, want to find a jumping off point from somebody that's doing something similar to you and use that as a guess. But again, the temptation is often to use too little test data because you really want to fit that. You want to train your model well. You don't want to deprive it of valuable data. Let me see, I've got a couple questions here. Test data. Okay, so question here is, it seems like the test data should be one use only. What do you do if you create your model, test it against test data, and find out that your model is not accurate against the test data? How do you proceed at that point? Well, that is where you have the validation data. The validation data allows you to keep playing around with your model and test it and use that to adjust lambda and k. Your test data, as long as it's never used, so in our case here, as long as our test data never feeds back into this process, it's okay to reuse it as a final check. So when you come to me and say, everything's done, here's my value, here's my U and P matrix, and here's my lambda and my k, and I test it against the data and tell you that's not good enough, you're only 80% accurate. As long as I don't give you the test data, I don't hand it to you, I don't show it to you, as long as it stays on the side of the wall, you can go back and do this process again, and all is good. So as long as the data never enters back into the process, all is good. You can keep testing against that data as long as you never see it. If somehow this data gets involved in this process and starts getting involved in U and P matrix, now we got a problem. And that's where, so in that sense, you can't use the data, one use data. But we can always go back, as long as this stays on the other side of a wall and is never rolled into this process, you can keep reusing and testing against it. And indeed, that's what you have to do, because this process is an iterative process here. We're going to always keep playing around with this. As long as this never gets back into this in some way other than just getting a single number out at the end and saying, here's our accuracy, you're going to be okay. And we'll see that, by the way, in the code that we're about to write. It'll illustrate this explicitly. Let's see what we have here. TRV and test must have very random. Let's see, several testing folds. Okay, are people getting, so these questions look like, are we getting into K folds here? And so it looks like a thread has spun off here that's heading in a different direction. I won't try to address that question right now in general terms. As a matter of fact, I think that thread is probably, if people are talking about doing something like cross-validation. So there are techniques, because again, data is so expensive and sometimes you just don't have a lot of it. There are techniques to try to slice and cycle the data up. So you slice the data up and use some of it for training and some of it for validation. And this is valid. This is called cross-validation. And there are ways to do this slice and cycle up to use the training data and the validation data. But you never, ever want to mix the test data in. If somebody tells you that their cross-validation scheme allows them to reuse and recycle the test data, well, they're treading on dangerous ground, because that is not what you should be doing. The test data needs to remain test data. People do this all the time. They think cross-validation, which again is a technique, we don't have time to dive into it in detail, but it's a way to take and cycle through your training data in slices and use some of it as validation data. But if you start actually using it with the test data, you have now strayed into the realm of potentially overfitting and having no way of knowing it. So cross-validation is not a magic way to reuse test data, although people do it repeatedly. Okay, so here's where our data comes into play. This is our process we've got, where we've got this sparse matrix. We're going to approximate it with this U and P matrix and up with a dense matrix, which means we're going to use We're going to start out and divide our sparse matrix into some, we're going to pull out some points for training data, some points for validation data, some points for test data. So we're going to slice this up randomly. We're going to pull out random users here, ratings, not the entire user, just some ratings for random users. So we're going to get random points out of here and pull them out and divide them into the training data, the validation, and test data before we do anything else. Then, as we train the model, and this multi-screen laser pointer is really frustrating. As we train the model, we're going to use the training data that we've set aside for U and P. So U and P are going to try to match the training data. That's what altering these squares is going to look at. It's going to look at the training data and try to make U and P match the training data. And as it does that, we're going to get some results along the way we can compare against the validation data. And if the results are good, we might say we're done. Let's move on and test the model. And if the results are bad, we might say, let's adjust some of our hyperparameters and see if we can do better, like K, for example. So if our results are really terrible using our training data to find U and P compared against our validation data, we might adjust K a little bit. We need a bigger K to get a better approximation. So we do that based on the validation data. We're all done, and we think we're ready to go to the boss and say, we have a great model. This works wonderfully well. Now is when we pull in the test data. So I put it off the screen here, suggestive of the fact it never enters into this process. Now the test data compared against this, and we can say, this is great. And if we say, uh-oh, this is terrible, then the test data never gets used for training or adjustment, because we go right back to this process just based upon some single number that we know from the test data, like it's 90% accurate, that's good enough, or it's 70% accurate, that's terrible, go back and redo it. So we never get to see the test data. It stays on the other side of a wall. So that's our process that we're going to do. So let's actually start writing some code here. Let's build our recommender. So in our case here, Spark makes it very easy to load and parse the data files. It's going to make it very easy. We're going to grab this ALS model out of our machine learning library. We're going to train it with variant Ks. The only hyperparameter we're going to search for in our immediate problem is K. I'm going to start with the value of lambda that probably works well enough, and we're going to find it does work okay. But we don't have the time here to explore the full space of hyperparameters, Ks and lambdas, or maybe some other hyperparameters we'll stumble upon on the way. We're going to just explore the space of K and find the best value for K. And we'll find that that's good enough, because I'm going to start out with some other reasonable numbers that we get a working system. And then with our working system, we're going to add in a new user and get some recommendations for the user. So we're going to explore K. In the real world, and if we were entering the competition and we had no idea what we're up to, we'd also have to find lambda and maybe some other hyperparameters. And indeed, that will be a homework problem for you. So if you want to follow along with me in real time, and I again suggest that you don't, that you more or less pay attention to me, you can fire this up and get moving the same way as yesterday. Once you're logged in, grab yourself a compute node with Interact, load the Spark module, and start up PySpark. I'm going to suggest that you don't do that, and instead you wait until the homework problems to work on this interactively so that you can pay attention. Okay, so let's do the boring stuff first, which is to load in the ratings file. Again, it's a human readable file.
John, there's a couple comments.
Okay,
There's a follow-up. As soon as you tell me the model is not sufficiently accurate against the test data, I am in a sense using information about the test data in the training model. There's a comment, and there were questions. But then how do you carefully select the test data, and what is the good splitting ratio between training, testing, and validation? 80%, 10%?
Let me just, sorry, Steve, let me get the first question first. It's an important one. You're right in the sense that you are in a sense, in some very, very, very indirect way, you are using the test data to go back, but you never get to see it. Let me put it in concrete terms for Netflix and their $1 million prize here. Netflix and their $1 million prize here said, you never get to see the test data. They never even release it. So it's not only up to you, you're not responsible for splitting it. You never get to see the test data. It never gets released to you. And so you have to submit the thing in, and then they tell you who wins. So that's the way in this particular case here that we really use the test data. Netflix never gives out the test data points. So you split off your validation data and use it to fit the model, and you submit it to Netflix, and they say who wins and who doesn't win. You don't get to iteratively go back and keep reusing the test data to fit your model. So you never in any way, so that's the proper way to think of it, is in the Netflix case, you never get even that result until it's competition time. So that's the proper way to do it. The test data never comes back, even in the sense that you get to try again. That's the best way to think of it. And And yeah, so just walk away with that as the model, because the Netflix one makes it very easy. And that will keep you from contaminating things, because yes, you could keep going back against the test data, lowering the value, and use that as a way to find hyperparameters, in which case you've invalidated the point of using the test data, which is to make sure your model generalizes the data you've never seen. Now you're somehow fitting the data you're using a test data to fit the model to. So you are correct. You should not go back after you've seen the test data results and use it. And again, if at any point in your future budding machine learning career, you start doing that, think of Netflix trying to give somebody $1 million and not getting sued by the losers, right? I mean, that's give $1 million out, you better have a good process. And Netflix's process is you never get to see the test data, you never get to run against it. And that's how this is supposed to work properly. So think of the model that way. Okay, Steve, what was the next question?
What is a good splitting ratio between training, testing, and validation? 80%, 10%, 10%, or is that a problem dependent?
That is one of those things. Once again, the best I can do is give you a rule of thumb that's very vague, and that's the state of the art. And in our case here, as we're about to see in this slide here, I'm going to split this into a 3-1-1 ratio. In other words, we're going to have basically 20% test and 20% validation data. And you can't really justify that in any really strong way unless you also want to do a bunch of experiments with different values and see which ones work out best. So that is a rule of thumb kind of thing. And again, people tend to set somewhere between 20%, 30% of the data to the side as the test data. That's again, a vague rule of thumb, but the best you can do is look at what other people are doing that are working on at least as close to problems to yours as you can find. So in some sense, that is a hyperparameter. Not in some sense, it actually is really a hyperparameter. It's how much you set aside. Not an interesting hyperparameter in other senses, but it is one.
And to clarify, the training data would be all of the data from the subset of people rather than only a subset of data from some people.
The training data in this case, well, let's look at exactly what it is in this case here. The training data, because this gives you can see it in code. The training data is us taking out of all of the movie rating data points. So it's individual movie ratings. We're not pulling out some users, not pulling out some movies. We're picking out random ratings. So individual movie ratings randomly out of the entire data set, we're going to randomly pick out 60% of them in this case. And that's going to be our training data. And we're going to set aside randomly of those points 20% for validation data and 20% for test data. So that's exactly, we're just randomly picking out of that file movie ratings. So this is the code to do exactly that. And again, we've got a human rateable file here. It's nice, we can just suck it right in with the text file command. Now we've got an RDD. Now we're in RDD land. We want to keep everything in RDD land as much as possible in Spark. That means everything is going to be working with all the parallel machinery behind the scenes. Everything we do is nice and parallel, which for the small version of this data set we're starting with here, maybe you think you can get away from your laptop. But if you're Netflix, right, everything better be running in your data center on RDDs, not ever as some Python variable sitting on your front end or your driver or your laptop, however you want to think of it. So everything's going to stay in RDDs until we're finally at the end generating results, user ratings. So we read this into an RDD, and now we want to parse this a little bit. So again, Spark is wonderfully convenient for taking enormous, noisy, polluted data sets with anomalous, error-ridden stuff in it and letting you quickly filter it. In our case, we don't have a lot of problems to deal with, except for the fact it's a text file, and we want to turn this into some nice integers to work with. So what we're going to do here is we're going to take each one of these lines of movie ratings we read in, we're going to split them with a map, and then we're going to take each one of the resulting entries which comes back, which are going to be 3 text things, and we want to turn the user text number into an actual integer, the movie into a nice integer, and the movie rating into a float. You might think the movie ratings could be integers because they're 1 to 5, but all of our ALS scheme and everything else can be working with floating point numbers. So actually we want to turn it into a nice floating point number. Everything's really floating point numbers behind the scenes. So when you spit out to users on your interface, it's a 4-star rating, you really know it's 4.213 stars or whatever. So this is our data right away in a nice mathematical form that everything's going to be able to work with. Now we want to split into 3 pieces. And once again, because Spark's meant for serious work like this, it of course has a random split transform in the RDDs transforms. And we're going to split this into 3 pieces here with sections of, like I said, 60% of the data is going to training, 20% to validation, 20% to test. Okay, now that we have these validation and test sets of the data, we want to make sure as we start to use them, we're going to strip off the actual rating. So later on, we go to compare against them. So in other words, later on, I want to have some data points. I want to know that this user saw Star Wars, but I don't want to know what the rating for it is until I compare it. So we're going to have our prediction RDDs, both a validation and a test version of them. We're going to strip off this last value, this floating point number, the rating. But we want to know what they are. We want to know that this user actually did see Star Wars. So later on, we can go back and compare our predicted value against the actual value that they really gave. So these are our prediction ones we're going to use later on. Okay, so we're off and running. And
John,
yes.
Is there a memory hit for keeping so many transient RDDs around?
That's a good question in practical terms. Spark is trying its best to keep everything in memory because it's going to be much faster. That's one of the huge benefits over Hadoop and other schemes. But of course, these things do take up memory. One of the neat things that Spark does in the background is that you might think when Spark gets rid of an RDD that it has to move it to disk or something like that. Instead, Spark actually is keeping track of the fact that if you look at what we're doing, we're creating RDDs, and we haven't gotten that far in this problem yet to make it so obvious, but really RDDs are derived from one another. It's really, we're building this graph. If we look at any RDD 2 pages down in our program, we're going to see that it was derived from earlier RDDs by mappings and filters and other kind of transforms. Spark actually keeps track of all these transforms. It does that for one reason, because we said it does this lazy evaluation where it waits to the last possible moment to do a bunch of transforms because that allows it to be efficient. But it also means if it decides that it doesn't have enough memory at some point and it says, say it throws out this RDD, it runs out of memory and it purges this predict test RDD, well, you know what? It knows how to create it again because it remembers this graphical relationship to work backwards. So Spark has this ability when it runs out of memory to throw things out, and then if it needs them later on, it can go back and recreate them. So yes, you're right, things start taking up memory, and we should always think of these things as enormous big data RDDs. And so creating these does take up memory, but it can always get rid of any of the interim ones that things aren't necessary anymore. So I keep creating these new RDDs. If it doesn't think this is necessary, it can get rid of it. And if later on it becomes necessary, it can go back and regenerate it because it knows this graphical relationship. So Spark can be pretty good and clever in what it's doing. So you shouldn't be afraid of generating interim RDDs because it can kind of go back and purge itself of them. Think of it as a kind of garbage collection if it doesn't need them. So don't be shy about making new RDDs if it makes your logic clear. It's not expensive in the sense that Spark will just get rid of ones that it thinks it can reproduce. And if it doesn't need to reproduce them, it just gets rid of them at no expense. So don't be stingy about using RDDs and think that, I need to do them all in one fell swoop. No, use all the transforms. It won't create them till all the transforms pile up anyway. So a lot of those interim RDDs will never exist. They all go away when it does all the transforms to begin with. But it's a good question. It's good to know how those things work behind the scenes, and it's good to see some of Spark's magic in action. Okay.
Is there a way to limit how much memory Spark takes up if I'm running something on a shared server?
Well, there is, but not from within Spark. I mean, so Spark, yes, whenever you're on a shared server, as a matter of fact, on Bridges, this happens all the time. You can set process limits and sizes and limit things. Right now on Bridges, for example, our default scheme is when you ask for an interact node, you're at the moment for this workshop only getting, I want to say 4 of the 28 cores. I think that's what we have it set to. And that means you're only getting that slice of memory. We can easily change that dial. So the system administrators can set things up so that the amount of memory that you're getting in shared resources varies. If you're on a cloud resource, that's happening all the time. When you're on a cloud and you ask for virtual, compute nodes, you're getting slices of a bunch of things on the machine. So all the time, the system and the administrators and you are setting, these configuration options. But inside of Spark, you don't worry about that. Spark's job is to use all the available RAM if possible, and then spill over to disk if necessary. So inside of Spark, you don't worry about it, but outside of Spark, it's a good practical consideration. And on Bridges, it happens when you type interact. And there are other options to interact that we don't want to bore you with that would allow you to ask for more memory, bigger memory nodes. You could, if you were doing serious work on Bridges with this, you might very well want to have one of our 12 terabyte nodes. And so with interact, you could ask for, a 12 terabyte node. So it's important. You do want to control that, but you don't do it within the Spark code. That's not the appropriate layer to do it. You do it when you start the Spark system up.
What is the zero argument for in random split for the three subsets?
What is the zero argument for? Geez, I forget.
Someone commented it is the random seed, probably the seed number.
Oh, that makes perfect sense. It's a random split. So, in Python, a lot of these things default to 0. So I wonder why I didn't just leave it out instead of stuck it in there. Maybe to make myself discuss it. It's been a while ago since I stuck that in there. But you are doing a random split. Once again, it's a random thing. If you want to reproduce this, if I want to go back later, if somebody questions my result and I want to go back later and reproduce it, if they said, I don't really believe you got 1.3%, I want to be able to go back later and get 91.3%. Well, to do that, I better be able to reproduce exactly the random split I had. So having control over the seed when you do a random split is important if you want to be reproducible. Most of the time, you maybe don't care about that at all. Nobody's questioning your results and you trust that the randomness isn't a big factor. But anytime you have a random element, it's a good practice to at least be aware of it. And so that is probably why I stuck this in originally, is to flag that and say, hey, if I want to be able to go back, if you dispute my results later on, or if I question my own sanity, I want to go back and get exactly the same results. Well, I better be able to exactly reproduce this random split of the data that I have. And that's important. Good question. I haven't thought about that in a while, but it's a good question. Good thing to highlight. Okay, as I'm doing this process, by the way, I am constantly checking it as a sanity check to make sure I'm doing the right thing. So I take some elements here and there, which is fine to do. Even if this were billions of elements, taking a few of them as a sanity check is fine. So I take a few of these elements here and there to see what's up, make sure I'm formatting the data right, make sure, in the end here, for example, is my training data. It says user 1 like movie 1029 with 3 stars. Okay, this is all good. And here's my prediction data. It says user 1 saw movie 1129, but I don't know how many stars it is, but later on when I want to check, I know this is one that we have a real rating for. So that's why this is a prediction RDD. So I make sure I know what I'm doing as I'm going along here. And
somebody comments, does it mean split rows, not columns?
No, good question. It means, so yes, so are we getting rows or columns out of our data set? And the answer is neither. We're getting points. We're getting movie rating points. We're not grabbing an entire user. So when we draw the data set as it exists on disk, as we read it into this RDD, is a bunch of individual movie ratings. We've also been thinking of this as a table, right? Because we think of organizing it into a table where we've got these rows of users. But the way it sits on disk, it's a bunch of random points from that table. And that's what we want to grab. We don't want to grab a whole user. And we don't want to grab a whole movie. Instead, we want to grab random ratings. So we grab 1 or 2 ratings for some user and 1 rating for another user, and some other user doesn't get sampled at all. So we're grabbing random points out of that table. If you want to think of the data as a table, it's sitting on disk as a bunch of individual points. It's not organized in a table, but if you want to think of it as the table, or ultimately our table ratings, our matrix, we're grabbing random points out of that matrix. Okay, so we've got our RDD set up. Now it's time to actually do the fun stuff, which is our ALS scheme. So we bring in ALS out of our mlib, and we have some parameters that we want to set up here. So we have ALS has a random element to it. At the very least, we have to initialize our U and P arrays to these random values to get the thing off the ground. If it was all zeros, nothing would happen, right? So we need to get some numbers in there. The seed will allow us to at least repeatedly control that. We have how many iterations do we go back and forth with ALS? We're going to do 10. Well, this is a parameter. Is that enough? Is that enough to get accurate? Or is it too many? Maybe we're wasting a lot of compute time. This would be very expensive. This is where the full-size problem, as you'll see, it takes minutes to do each iteration with the full-size problem. So do you want to sit around all day needlessly? Not if you're Netflix. So how many iterations should we do? It's another hyperparameter we should investigate. We should actually graph, and we investigate these things by drawing various graphs empirically. So for example, with iterations, it's a homework problem for you later on, is you can graph the error as we do this and say, oh, by the way, the error gets to be reasonable after 5 iterations. You're wasting your time with the last 5. Or at 10 iterations, maybe the error is obviously still going down. And you go, we could do better if we went to 20 iterations. So how many iterations should we have? This is our regularization parameter, lambda, which, by the way, don't call it lambda, because lambda stands for these lambda things. It's a keyword right here in Python. So I have to call it regularization instead of lambda. Trial ranks, the ranks that we're going to try for K is going to be 4, 8, and 12. and we're gonna find our error. So I initialize our error to some lowest, to infinitely low to begin with to get it off the ground. Then here is the interesting part. So here's our loop that actually does the interesting stuff here. And it's a mix of interesting stuff, and then it's a mix of some boring, but maybe maybe good exercise, juggling of the RDDs to massage our data into the right form. So the interesting part of this loop is that it trains this model, and we'll step through this. So don't fear if I'm going fast here. We're going to step through this.
John, real quick. Isn't each row a random user/movie rating, i.e. a point?
Okay, well, let's define row here. So a row in the text file, yes, is a random. So if you read in a line, so let's not call it a row, it's called a line. A line in the text file, the movie ratings file, is 1 point in our table, our ratings table. It's one individual movie rating is a line in what we read in. And it's an element of our RDD is one individual rating. When I think of row or column, I think that the sensible way to think of that is an actual, our spreadsheet of user ratings. I think of a row as being a user, and then all of their ratings are the elements in that row. So that's the way I've been using row, here. But if you by row, you mean a line that we're reading in the ratings file, that's what I think of as a point, an individual movie rating. So and if there's any confusion, take a look at the text file that you're reading in, or print out at any point in time any of the elements of the arrays that we're dealing with here. Always good to do is Spark makes it easy to make sure you're doing the right thing. So we're going to find the best K. That's our objective with this test here. We're doing a hyperparameter search to find the best value of K in our trial ranks here. So 4, 8, and 12 are the 3 values we're going to try, and we're going to find out the best value of K. So to find this hyperparameter, we need to, and we're starting out with these other hyperparameters, assuming that they're pretty reasonable, but maybe we should investigate them as well. And indeed, that's a homework problem for you, but we're going to assume they're workable. And we're going to find the best value of K, at least nail that one down. So again, the high level quick view that we'll step through here is that we're going to train the model using ALS, giving it this training RDD, and we're going to try different values of K. And it has this seed because ALS needs to start the arrays with random values. It has a number of iterations to run, and it has this regularization parameter built into ALS, our lambda value. So this is what we're going to do. This is all the action of training it. Now, after we train the model, we can get some results back out of it to test and see how well it fits our data. So as we do the predictions here, we can get back out of the model some prediction RDD, and then we want to get the error by comparing our predictions RDD with the actual ratings that are given by it. We'll step through this now individually, but I just want to give you the overhead view first, what it's doing. So we go through this 3 times, and we find for the various values of K, we find the 3 errors that we get. And it's the root mean square error from the whole array by comparing it, again, using our error term here, element by element. So this is what we get for the errors, and we're going to step through 3 values of K. And we're going to find the best value of K. So let's step through what the logic is in here, because this is not interesting in a machine learning sense, but it is a good exercise to see if you can follow along with what's happening with the RDDs in the Spark sense. So make sure you can, if you want to say you're comfortable with Spark and RDDs, make sure that these boring details here make sense to you. And the idea is that if we look what the ALS training routine gives back to us, so after we do the model prediction step right here, through the training step, and we ask for it to predict things, what we get back from the predict all from the model is it will spit back a bunch of tuples, labeled tuples that look like this. They actually say user, product, and rating for each of these user, product, and rating. So we get these values. So it says in this case, it's going to predict that user 463 likes movie 4844 is probably going to give it a rating of 2.7 stars. And user 380 is probably going to give movie 4844 a rating of 2.4 stars. So this is the kind of stuff that we get back out of the model. These are all, and it'll give us all the predictions here. Now, we need to get this RMS error out of it to see how well we're doing. It's up to us to do this. So for us to get the RMS error, what we'd like to have at the end when we finally do the math here, so we want to get from what the model gives us back to this line here that does the math, what we'd like to have is a bunch of elements that look like this, that have user rating, and then the given rating that we know we were given in the real data set, and the predicted rating right here. This makes it nice to do the math, right? This gives us the error for this rating. We can get the error for this rating. We can get the errors very easily. So we want to get from this form to this form. And to do that, that's what the next 2 lines do. So this is a good exercise for you to make sure you follow along with how Spark works in massaging RDDs. It's not interesting in any machine learning sense, but it's a great exercise in the do I understand how Spark works, sense, how RDDs work. And so let's look at what happens here to get from here to here, because we have a number of methods here strung out together. We have some maps and some joins going on here to get us from here to here. And they're good typical examples of how to do that. So what we have here is we want to take our predicted all ratings, which have everything stuck in there, and we want to strip them out a little bit. So this mapping right here says, just give me back the user and the rating in one tuple, and then stick on the end of that. So this gives us a key of user and rating, right? If we get into a form like this, this is actually a key value RDD, which means we can do some key value operations. And particularly, we want to do a join to combine these together. So what I'm doing is I'm massaging this into a key value RDD is one way to think of it, by forcing this into a key value form that I like. It says use the user and the movie as the key, and that makes sense because that really defines a rating that we want to look at. And then the value of it will be the rating. So that's all I've done here is I've forced our predicted values into this form like this. So it's nothing different. It's just a different form of the data to make them a nice key value. User rating is the key, or user movie is the key, and the rating is the value. Okay, that gets us halfway there. And I make sure I know what I'm doing here by looking at these as I go. Now, I want to do the same thing with the validation data is already in this form. User, movie, rating, right? These are the ones that we're actually given. We know these are correct. Now, the next thing to do is to combine them together. And if I say, how do I want to combine these together? I'd like to take this and combine them together to get this. If I look at this, this turns out to be that join operation from yesterday. And remember yesterday when I said joins really, if you've never seen them before, look like a weird operation. How often are you going to use that? And I said, well, you can find yourself using it a lot. Here's a perfect example. We've got two RDDs that we want to combine the values together so we can do further processing. That is exactly what that join operation does. Takes all the common and only the common key value pairs, because we don't want things that there's only a prediction for, but there was only a rating for, but there was no prediction. We don't care about those. They can't tell us anything. We want the ones where we know that we have a prediction for. We want to take those pairs and we want to spit out at the end all of these things now that we can compare. So this is all the things that are possible to compare, all the movie user ratings that are possible to compare, and we've combined their values now. And this is nice. This gives us a trivial thing to do math-wise now. So our next line with math working on this RDD is just root mean square. That's all this next line does with the math. It just does a root mean square here, but it's because we massage things in the right way with a join. So again, I think of this as incredibly boring from any machine learning perspective, but if you're new to this, I think it's illuminating that once again, a join operation pops up. And once again, you can see that Spark makes it very easy to massage our data into the right format to do these database type of operations and to do them in parallel too. Again, you could, if you think, oh, it's a join and whatever, why am I not doing this in my Access database on my laptop? And the reason is because this stuff can all happen with billions of points at scale. Okay, so assuming that you followed that, and again, pick your way back through those slides if you have some questions and
John,
make sure you understand. Yes, questions.
Does the math line pull all the values of the RDD into memory?
Okay, so there's the math line, which is right here that does math right here. This does not. This is going to do everything by pulling to the memory. If you mean, I assume the user means the very good question of, does it pull everything back to the driver, to the front end and do things in memory in Python, basically? No, this all takes place in RDD land until it finally comes down to a scalar variable, which does come back into Python memory. So this is all happening in RDD land, these root mean square things, and then we get this mean out of it. So the mean is an operation that takes place in RDD land, at which point we're down to a single nice scalar variable that we can take the square root of. So this part all takes place back in RDD land, which means again in parallel behind the scenes on distributed computing nodes until it finally turns into a single value, the mean. So this is a nice action that we have available to us on RDDs. So at that point, it's all been reduced down to a single value, and we can just do this boring, normal, math routine of square root on the front end on a single number. So this is all RDD, and until we get down to a single number, the mean, and then this is a single nice scalar variable on Python. So it's exactly what you want to be scalable and to be efficient. Okay, so we've now found 3 values of k, and it turns out the best value of k is 4. Now, that's undeniably what this is telling us, but this is also kind of surprising. At least it was to me when I first did this. I said, the best value is 4. 4 is kind of not the, I thought the best value of K was going to end up being the widest value. The most accurate value would be the wider values of K. And I ended up with 4. And I double checked it. Indeed, it is 4. And I said, okay, well, that surprises me. I wonder what's going on here. And I then tried it on the larger, the full-size data set, which you have available, the large movie data set. That's actually the Netflix full-size one, which takes longer to run. That's why we're not working with it immediately on the first pass. And I looked in the full-size data set, and indeed, it turns out that K equals 12 is a better rank, which is what makes kind of more intuitive sense to me. So the fact that the smaller K worked best here is mostly, and these are all very close errors too, is mostly an artifact of this being a very small sample of the full movie data set here. This is only, I want to say 50,000, however many movies. It's not many movies. And so K ends up working well for 4. But that is a little counterintuitive. And it turns out as we go to larger movie data set, it ends up being K at 12 does work best, which kind of was more to my expectation. But it's good that we explored this. You can't let your intuition just let you pick values. And by the way, maybe I should go larger than 12. And when I found out that the large movie data set worked with 12, maybe that suggests maybe I should try 16 or 20. So this is a hyperparameter that still deserves some further investigation, perhaps. Okay, at any rate, we think that 4 is certainly workable. At least it gives us an error of less than 1 star for all of our ratings right here on the small data set, which is pretty good given it is the smaller data set. Let me see, I have some questions here. Do any of them, I'm trying to read quickly. Increase the iterations. Will we find another best value of K since RMS? You might be, yes, the iterations, if we increase iterations, we may be driving the error even lower. So increasing iterations might be a way to find a smaller value of K. The hyperparameters are always interrelated. So that's a very good idea here. It's something to investigate. As a matter of fact, you've guessed one of the homework problems. Let's see, calculate the error. You don't differentiate whether the original rating is blank or not. Calculating the error, if the original rating is blank, we set it equal to 0 is what ALS does. We also make sense check values of regularization in conjunction with K. Well, we should absolutely check values of regularization, but if we do them all at the same time, we'll confuse ourselves silly. We got a parameter space search, but you are right. We should check some values of lambda. I just pulled that 0.1 out of somewhere. You should verify that it's reasonable and maybe optimal. Maybe it's not. So you are absolutely right. These things are interrelated. We don't want to investigate them all at once. We'll just confuse ourselves. But it's a parameter space search. Which applies to lots of areas of science, right? Where you got multiple parameters and you got a space search, and we got multiple dimensions here going on, right? We got K and lambda, iteration count. We got a lot of things that we got to juggle, and we should investigate them all more fully if we want to really say we know what we're doing and we've picked reasonable values. You're absolutely right. Welcome to machine learning, where investigating the hyperparameter space is the biggest part of the problem. But at the moment, we're going to move on because we think we got something that's giving us some reasonably decent errors. But these are all good suggestions. Considering multiple hyperparameters or grid search style syntax rather than say nested loops. When we get into deep learning this afternoon, we'll look at the fact that these hyperparameter searches do have some nice frameworks and some nice workflows to enable them to do a grid search, and again in multiple dimensions. And maybe your grid search, you don't want to be so linear. Maybe you're trying to even find some orders of magnitude of a hyperparameter that you're just jumping into. So yeah, there are some better organized ways. We're doing this in a very simple and obvious way right here for K. But again, if we were looking for all these hyperparameters at once, we might find out we'd want a little more sophisticated of a framework. And we'll find this afternoon with deep learning that there are indeed those frameworks exist for us to use. So good question. Okay, so we think we've got a working model right here.
John, there's a couple questions that have gone by. Did you answer in calculate the error? You did not differentiate whether the original rating is blank or not. Did you address that?
Yeah, I did. I think
Okay,
I got that.
would it also make sense to check values of regularization in conjunction with K?
Yeah, just talked about that.
Is there a way to tune all the hyperparameters at the same time?
Yeah, got that. So
How do you choose the initial trial ranks to try?
how do I choose the initial trial ranks to try? You can think of it as I pulled it out of a hat. And maybe, because again, it's another hyperparameter, and we got to get off the ground with something. And so that's what we pull out of that. Maybe these would have, if I picked really inappropriate values, which the first people investigating this algorithm undoubtedly did, I'd find I get really terrible errors. Maybe this needs to be 120, needs to be my smallest K. I wouldn't be hard to believe given how huge these arrays are. Matter of fact, I'm amazed that this stuff's workable with these small numbers, right? So I only know that these are reasonable because I got some reasonably small errors. I'm getting less than a star error, which I think is okay to get moving on this problem. You know, it's my best guess, but definitely these need more investigation. So I love the fact that you all keep asking questions about hyperparameters and because this is exactly what you will be asking yourself as you get into machine learning and you work on problems all the time. How do I get a good hyperparameter to get this problem off the ground? Did I really find the right values? Am my runs taking 10 times longer than I need to because I have a bad hyperparameter? I'm not even getting any reasonable errors. I just can't even get this thing to start to converge. What hyperparameters are really wrong? This is the world of machine learning. That's why the very last slide of today will be from a really interesting paper with a complicated deep learning model, basically explaining they spend all their effort looking for hyperparameters. And that's maybe the most important thing that people publish. If you look at the papers that people publish on the leading edge of machine learning, they make no small, they are very proud of the fact that they found usable hyperparameters to allow people to piggyback off of that research and move it forward. They explain them well in the paper, they explain how they found them, and they say, hey, you know, this is maybe the most valuable thing I'm giving to you is this set of usable hyperparameters that you can move forward with. So it's good that you're wondering about these hyperparameters because you are sure going to continue to wonder about them as you do machine learning.
And I get a different value of RMSE than you for the testing data. Is this dependent on some random seed?
Well, there is a random seed, but if you're using mine, although let's see, I set the random seed here. So if you're using my random seeds, you should get the same results. So you should get this. I don't think I've left any random seeds out. If you leave them out of these routines, then it goes and it uses different, different ones based on different runs and everything. Assumes you even want different ones from one iteration to the next. So I think you should be getting the same results as me. If you're within a couple decimal places, we won't sweat it right now. Maybe there's, but I think I covered all my bases with random seeds to reproduce this from one run to the next. But who knows? Maybe the library got updated since I did this slide or whatever. As long as you're close to these results right now, don't sweat it because you can see these are pretty. Our star ratings are only good to 1.5 decimal places at best anyway. But for repeatability purposes down the road, you should be able to repeat your own results at least accurately, or else you somehow have a random seed running wild, that's still not nailed down. Okay.
What if you also have users' comments? How do you combine numerical numbers with text?
How do I what if user? Oh, users' comments on movies. Oh, well, you can keep text strings along in RDDs. RDDs are very compliant. You can have anything in there you want. If we wanted to bring along text strings, we could. And as a matter of fact, at the end of this, because we want to spit at least movie titles out, you'll see us roll some text back into our RDDs. So we'll give you an example of how to bring some text back into this. And you could certainly do that. And users' comments, for example, in a modern application today, you'd probably want to do sentiment analysis on those, which we'll talk about later with deep learning. So, yeah, I would probably maybe want to keep users' comments in a full-blown application today. And we'll see some text brought back into this when we're done here, because we would like to give the users some real movie titles. So, we'll get to those points kind of. Okay, but to get back to these points right here, we think we've now got a model that works. We think we got some reasonable parameters here. We think that if we use a rank size of 4, it's going to work pretty well. So now let's go ahead and actually see if we can test and get good results testing this. So here's why we think we got a working model. Now it's time to actually see it. This is when we send it off to Netflix and see if we win the prize or not. So this is how we're going to evaluate it here. We're going to do pretty much the exact same thing we did up above, comparing against our validation data, except now it's time to use a test RDD. It's the only difference between these two. Up here, we use the validation RDD. Now we use the test RDD, the data we set aside at the very beginning and we haven't touched or used for any of this process or anything else. So now it's test time, or send it off to Netflix time if you want to think of it that way, and they do this for you, and you never get the benefit of this. And now we run our test, and we find out our testing, our error is about 0.94 stars. So that's the real accuracy we can actually claim for our model. All this stuff up here, we may have inadvertently been, overfitting our data. This is some data we couldn't possibly have overfit because we never saw it, and we never get to see it. Netflix, doesn't release this till the competition is done, kind of thing. Okay, now we think we got a good enough system. So let's go ahead and add a user in and get some ratings for them. And so this is a good check on your Spark skills. We want to create a new user, ID 0. And I wasn't sure if there was a 0 in the database or not. So I just quickly checked through the database, said, hey, is there a user out there? Took me a second to find out, no 0 user. So for user 0, I made up some movies and some ratings for that user so that we could begin to extrapolate off of that user. So here's some movies and some ratings for them. Now I need to turn that into an RDD so that we could start to integrate it in with things. So I just turned it into an RDD with Parallelize, and I unioned it with the ratings RDD. So now we've got all the data. We've got our existing ratings. By the way, now we're using the full data set. We don't care about splitting it into training and test and whatever data. We're past that point. We think we found a working algorithm, good hyperparameters. So now we're going to use the full data set. So we take the full data set, add this user into the full data set, and now it's time to retrain. That's one weakness of this particular approach, and it's probably a serious weakness in a production environment, is that every time we add a new user in, we have to go back and retrain the entire model, which is where the computational effort is, but that's the way this works. Now that leads us to think, are there better ways to do this, or how can we mitigate at least this huge step? Because Netflix certainly doesn't want to retrain their entire model every time somebody signs up. So, or adds a new movie rating for that matter. So we got to retrain to add in new movie ratings, but that's the way our scheme works at the moment. So we retrain. At this point now, we've got a new model. It's trained. We think it can do some predictions, but we're going to be a little bit nicer to the user than just spitting back a bunch of raw numbers at them. So let's go and grab the actual movie titles that are sitting in that movies file, and that allows us to match the movie titles with their numbers. So we grab the movies, and I think I take some things as I do this to make sure I know what I'm doing here. So we grab the movies, we parse them here, we split them into what we care about, which is the movie string and the movie number that it relates to. So now we have our movie IDs, and we can go ahead and now we want to match this up with the actual predicted movies. So, and again, as I'm doing this kind of thing, I take things as I go along here and make sure I know what I'm doing. So let's look at the movies that the user, our new user, has never seen. We want to get the movies they haven't rated. Those are the ones that are interesting to us. So we go ahead, and this is not an RDD here. This is just a little Python command here that says, let's create for this new user movies that they haven't seen by filtering out all of the movies that they have seen. So now we want to get an updated model predictions for all the movies that they haven't seen. So this is basically generating all the movies they haven't seen. We're going to ask for predictions on. So we're getting predictions on every movie they haven't seen. And now we end up with an RDD with all the movies that they haven't seen. So now let's go ahead now and let's see, do I have a little take here as I go along to make sure I'm doing the right thing. So let's go ahead and combine our movies. So this right here happens to be the movies that they've seen here, our user, our movie rating, and the title. And we want to go back, excuse me, this is the movie number, the rating and title. And we want to combine that and format it so that it comes out nicely here. So we, where's the join up here? So here's the join where we combine the movie ratings, and this allows us to now begin to get rid of the label or the number that we're labeling movie with. So we get rid of the movie number label. We now format things nicely here because what we want to spit out ultimately is just the movie string and the rating for the user. And now we can pick the top 10 of those. So if we do a take ordered on this, so we're going to take and sort on the values here and take the top 10. So that's what if we go look at take order, it says take ordered, give me the top 10 out of that, sort them in highest to lowest order. So that's why we have a negative here. So we're going to sort from highest to lowest order. And if we do that and we spit out the top 10 of those, we're going to find that this particular user here likes, well, would predicted to like, their favorite movie would be, I think this is a badly formed string for Maelstrom here, actually. I wonder why it's goofy like that. It probably corrupted a database. Maelstrom, 6.2 stars. King is Alive, 6.2 stars. So these are their top 10 movies, down to Business of Strangers, 5.8 stars. And if we want to pick a particular movie and see what they might think about that, we can go ahead and say for Lone Star, let's make a very small little RDD out of it that we can ask the model to predict on. So we create for movie number 800, a single prediction RDD, and it tells us that this user would probably like the movie Lone Star with a rating of 4 stars. That's its prediction at least. Okay, so we now have a working full prediction system. You can go back and step through all of these things and make sure you at least understand how the RDDs are massaging things. If you're confused at any point in time, pull things apart, take some elements. It's a good exercise to understand Spark. Like I say, there's two components to this exercise, one of which is a Spark exercise, one of which is an ALS exercise. By the way, the other day when I said we really want to sort on keys, I'm violating that rule here. I'm actually sorting onto values here. Oh, geez, I'm breaking my rule from yesterday. The truth is, take ordered. If you look at what it actually does, it swaps key values, sorts them, and swaps them back. So it's a nice fake out for the saying we really always want to work with the key values to sort things. That's kind of a workaround for it. It does for us, the swapping the keys like we had to do ourselves yesterday, or sorting and then swapping them back. Little detail there.
Couple questions.
Okay, what are some?
In this example, it appears that the best model is trained twice. Is this correct? Is there a way to save the best model during parameter search?
The best model is indeed, yeah, saved twice here in the sense that, let me back up. So yes, that's a good eye in that what we're doing here is we spent time training to find the best model here to find a value of K4. And then down here, we trained it again. So yes, why did we do that twice? Well, the answer is, say the models you can assume are big and expensive to keep in memory, and we probably are doing a lot of values of K. So while you can indeed save models, it's a good question, it's a good thinking here, you can indeed save the models, and we could save different models here, but in general, you would expect that these models are big. They're the entire U and P arrays, and we might also expect that we're testing hundreds of different values of K. So maybe it's best, so maybe in practical terms, you don't want to save it, you'd rather go back and recreate it. But maybe you say this training takes so long, I can't stand it, and I'd rather save the models, and then when I'm done, just keep the best one and delete the other two. So yeah, you could do it that way. And I didn't want to confuse this logic with doing saves in here. Plus, like I said, many times you're actually trying dozens of values of K out, and the models themselves are huge. So you don't want to have dozens of models hanging around until you can finally figure out which one you want to keep. But yes, that's an alternative approach. Okay.
Unless I missed it, I didn't see at any point where we normalized the ratings to be a normal range between -1 and 1. For most machine learning algorithms, shouldn't we be normalizing the data?
You are very astute here. You did not miss it. We didn't do that yet. But guess what you get to do for exercise 1 of the homework problems? You get to do exactly that. Yes, our movie ratings are not between 0 and 1. So here, you're one sentence ahead of me here. Our movie ratings are absolutely all, they're higher than 5. Now, if you think about it, right, this makes perfect sense, right? Our ALS algorithm doesn't know anything about a ceiling for the ratings. So as it was fitting the matrix, it found things that are, higher than 5. It generated things higher than 5. And it makes perfect sense, again, if you, think about, as I say right here, if you got a friend that likes anime, so all of her movies are very highly rated for anime, and she really likes Scarlett Johansson a lot. Well, geez, Ghost in the Shell, which is a Scarlett Johansson anime-based movie, might be one of those 7 out of 5 ratings, right, as they say on the interwebs. So it makes sense that our ratings would go past 5. Now, on the other hand, as this person observed here, Netflix normalizes things, constrains their ratings to 1 to 5 stars. So can you normalize these things appropriately? That's your homework problem, is for you to normalize these into a 1 to 5 star range in a way that makes sense. You don't want to, probably, if you think about it, you probably don't just want to cut things off at 5 stars. Maybe you do. But at any rate, that's a good question and a better exercise. Another exercise is we've got, like I said, a number of hyperparameters around here that we haven't investigated. And so one of them, for example, is iterations. And iterations is a good, simple way, straightforward, to begin to understand how you find these, because what you would do, let's run this problem multiple times with different iteration counts and see a curve. When you're finding these hyperparameters, is usually a matter of drawing a curve and seeing how things behave on that curve. And so in this case, to find the appropriate iterations, you want to draw a curve against the error and say, okay, maybe after 5 iterations, we really drove the error low and the last 5 are a waste of time. Or maybe after 10 iterations, that error was still plummeting and it looks like we have a ways to play out on this curve and we should go further. So you get to investigate that. Likewise, I mentioned that, I was surprised initially that the best value of K was 4 instead of 12. And even, by the way, 12, when we look at the size of these arrays that we're approximating, our arrays are, these tens of thousands by tens of thousands or millions by hundreds of thousands. The fact that you can work with such a small size of K is pretty amazing to begin with. And again, K represents how many latent effects you're capturing here. And also I should mention, because I don't think I did, that for users, we've talked about the latent effects. For the user in the, you notice these two arrays we're calling U and P, and ALS even calls them user and product matrices. That suggests that those two approximation matrices actually have some kind of life of their own. And indeed, the user matrix is where the users are kind of captured. And for users, you might think that those latent effects do represent things like how much the user likes science fiction or certain directors. Although again, you'll never pull those out explicitly. For movies, they represent things like, what genre is the movie or what actors are in the movie or whatever. And again, it's kind of surprising you can get by with such small Ks and get workable solutions, but that indeed is the case. You get to investigate that further. And if you really want to get a better handle on it, I think you need to move up to the large movies data set. Now, we didn't copy that because it is a good bit larger. It's many megabytes. So we didn't copy that for all of you into your exercises directory when we copied that over. It's sitting back there in training for those of you that want to investigate this. So for those of you that want to do exercise 3, go back and grab the large movies data set. And it takes longer to run. It's another reason we didn't do it on this toy problem is these the large movie ALS training takes a while, as you would expect. And so go back and give it a shot and investigate, values of K, and maybe 12 is even too small to really be optimal for this large data set. Maybe it should go larger. But at any rate, it's another hyperparameter for you to investigate. And again, hyperparameter investigation is where all the effort is really spent in machine learning. And we'll see that remains true with the different styles of hyperparameters this afternoon in deep learning. We're moving to neural nets. Neural nets, an extremely different approach, looks very, very different, means a different software framework, but these general principles that we've, introduced yesterday, emphasized here, introduced some new ones here, they're going to carry over into deep learning. And it benefits you greatly to understand them in different models because you really do have an understanding of them then if you see how it works across different types of models and paradigms. Okay, with that, we're officially at the end of the content, so I can go back and more casually answer some questions here. Normalize ratings.
Just the last one. Can you use ALS to do e.g. MNIST classifications?
ALS to do MNIST classifications? We are going to get into MNIST. So this is definitely a little look forward reference here. MNIST is some images, digit images we're going to use this afternoon to do character recognition. And we're going to do a technique. It's going to be a couple of techniques. They'll be very effective. And we're going to look at a wide range of techniques to address this. And so I circle back to even clustering to do MNIST and PCA. One of the things I don't mention is ALS, but you actually could use ALS to find yes, you could. It would be an even crazier problem. I'm going to mention many approaches to do MNIST. The many I mentioned is not ALS, but ALS does in the sense, since it's finding eigenvectors, you could use it. It'd be crazy and it would be more abstract. So for those of you that aren't really experienced in machine learning, it would be hard to see how it's even working. But yes, you could technically use it. And now, because ALS is meant to work on huge arrays and MNIST are tiny little dense arrays, fairly dense arrays, it would be a poor application of it. But in principle, it could work. We'll come back to this topic this afternoon because, like I said, we're going to look at the MNIST data set in great depth. And we're going to try many, many different techniques. But theoretically, it actually, could work. In reality, it's a ridiculous approach, but theoretically, yes. Let's see. We're practicing this exercise to get stuck or have some doubts or way to contact for any clarifications. Well, if you do have questions, you can contact me directly, and I'll be glad to help you through. So that's an open-ended offer. Please exercise some discretion there. There's a lot of you out there in these classes, you can see. So I definitely do not want to help with software installation issues on your laptop or something like that. As I said, these software stacks are tricky. And so that's the reason we're using bridges here. So please do not involve me in those kind of issues because I am very often unable to help and they're ugly and difficult. So if you want to take any of the software, all of the software you should, every single line of code we've done so far is open source. Take it back, run it on your laptops, other environments, and everything else. But please don't ask me questions about installing and getting this stuff running. That is a whole, they can go from being incredibly straightforward and simple to being incredibly painful. You might just pop a container in and it works great. You might find out that Python software stacks, this might be your introduction to the fact that they're insanely interdependent and moving targets. And it can be really painful to build stuff from scratch and ground up. Don't involve me in those questions is what I'm saying. Otherwise, I'm delighted to help you as best I can as you move forward into using this knowledge in your own projects. So please do. And by the way, I'm also even more happy to hear from you about your successful uses of this in your own projects. It really makes me happy to hear from people when they give me updates and let me know this was useful for them in some particular way. That's beyond the evaluations, which I hope you will all fill out after the workshop's over. So yes, please feel free to contact me. Oh, my email is urbanic@psc.edu, urbanic@psc.edu. That's scattered around, shouldn't be hard to find if you didn't catch that. And we're now closing in on our break. So once again, the lunch break is the one break that I'm not going to be hovering in the background for. So those of you that want to work on exercises or whatever, feel free, go ahead. Those of you that want to actually take a break, please be back at the top of the hour because we have a ton to cover this afternoon with deep learning. We're going to put the pedal even more to the metal in terms of getting into these machine learning mindsets and algorithms. It's a lot of stuff I've crammed in. It's a lot of new stuff this afternoon, a lot of new stuff. If you compare this to the last iteration of this lecture, it's an astounding, it's the most I've ever really incrementally updated things in one workshop to the next. And so it's because there's so much exciting stuff going on. So we're going to cover that at 1 o'clock Eastern time sharp. We're going to get started fast and we're going to get moving fast. If you're late, you're definitely going to few questions here. I don't see any pending questions here before I leave. And then I'll see you all back here at the top of the hour. So enjoy your break.